Around 1600 AD, Galileo Galilei was experimenting with dropping objects off of the Leaning Tower of Pisa. Um, and through the observations he made when he dropped these objects off the Leaning Tower of Pisa, he came up with this law of falling. And what Galileo said was that if air resistance was negligible, any two objects that are dropped together at the same time will continue to fall together, and their speed is entirely independent of the weight and the material that the objects are made out of. So it said that everything kind of falls together and it basically accelerates down together. About 100 years later, Isaac Newton, came along and he tied this in with his theory of gravitation, and he um, showed that this is due to the gravity, the gravitational force that the Earth exerts on objects on its surface is more or less constant. But he brought into a couple other little things here which we need to neglect other than just wind resistance. So what free fall is, what we define free fall to be, is this movement under the force of gravity only. So if we neglect, oh, by the way, so here's a picture. If we, that if we drop something in air, like a hammer and a feather, the hammer hits the ground first, right? But this is actually because of the wind resistance taken into consideration. If we neglect wind resistance, so we put it in a vacuum, meaning there is no air, there's nothing in there, and then the hammer and the feather will fall at the same rate and hit the ground at the same time. This is actually shown during Apollo 15. Commander David Scott took a hammer and he took a feather on the moon, which there's no air on the moon, so it's a vacuum, and he dropped them both from the same height at the same time, and they hit the ground at the same time. So if we neglect, so it showed this was true. If we neglect wind resistance, so the things that we ignore or neglect, say that they are negligible. We neglect, one, the air resistance. And two, we have to actually neglect how close we are to the Earth, the proximity to Earth, to Earth's surface, really, to Earth's surface. And we also have to neglect the rotation of the Earth. Then if we ignore all of these things, the biggest one is by far the wind resistance or the air resistance that we have to neglect. If we neglect all of these things, then all objects will accelerate towards the Earth at a constant rate. So this rate at which they will accelerate towards the Earth is going to be, so the acceleration in the y direction. Let me give a coordinate system here, which we have, I call a positive x to the right and a positive y upwards. Then the acceleration in the y direction due to the force of gravity is equal to 9.8 meters per second squared downwards. So we can call this negative 9.8. Now, we refer to this number, and this varies a little bit on Earth. It's not exactly 9.8 everywhere, but it's pretty close. And we refer to this number as g. So g is the acceleration due to gravity, and it's a vector quantity, and it's 9.8 meters per second squared, and it is downwards. Oftentimes we use a traditional coordinate system like this, positive y being upwards, and so then the acceleration due to gravity is negative 9.8. But it's very important to note here that g itself is not a negative number. G is actually the magnitude of the acceleration, which is just this 9.8 meters per second squared, and has a direction downwards. If I called positive downwards, then g would be a positive 9.8. So it's a vector quantity, and its magnitude is 9.8 meters per second squared. So this is the rate at which all objects on the surface of the Earth will accelerate towards the Earth, regardless of the shape, size, or anything, so long as we neglect air resistance, how close we are to the Earth, and the rotation of the Earth, rotational motion of Earth. Okay. So with this, we can use this acceleration is clearly a constant, so we can use the kinematic equations, and you can use them in the y direction here, and it's just now we have another given. If we drop something on Earth, we know what the acceleration is automatically. It's downwards 9.8 meters per second each second. So take, for instance, a ball which is dropped, as we have in this figure here. A ball which is dropped, and we have our coordinate system which says, at time equal to 0, y was equal to 0, v was equal to 0. This is dropped, and it looks like our velocity is becoming negative. So it looks like the coordinate system is right here. Okay, so we have a positive y going upwards and a positive x. Not that the x matters, is to the right. Now we can use our kinematic equations. We can use v is equal to v naught. Actually, let me put a y subscript on here. This is vy is equal to v naught y plus ay times time. But since this is dropped on Earth, we know this acceleration in the y direction, we called positive y being upwards. This means that vy will be equal to v naught y minus gt, right? And v naught y, we actually said, since it was dropped from rest, this was equal to 0. And so our velocity will just be negative g times the time. So you see, with g being 9.8, after 0.1 seconds, the velocity is negative 0.98. After 0.5 seconds, it's negative 4.9. Same thing we can use for delta y. We have delta y is equal to v naught y t plus 1/2 ay times the time squared. Again, with v naught y being equal to 0 and acceleration in the y direction being equal to negative g, negative 9.8, then we have delta y will be equal to negative 1/2 of 9.8, so we have negative 4.9 t squared. And so then plugging in these times here, you'll see that we have, these will give us the y values. There's a negative in front of this one here. My x covered it up. So that's how we can get all these numbers here. If we make a graph of position versus time, we can see that we're starting at rest, and the position is moving down. It's quadratic, right? So it's moving down with a squared. The velocity versus time, this was a constant. The acceleration is a constant negative value, constant negative 9.8. Therefore, the slope of velocity versus time is a constant negative, and the slope of this is negative 9.8. So this is free fall. Objects fall only under the influence of gravity, so they accelerate downwards at 9.8 meters per second each second. We can go a little bit beyond this, and we can look at throwing something upwards. So let's say we have in this figure somebody's starting out here at y equal to 0, throwing a ball upwards with an initial velocity of 13 meters per second. And it goes up to some top and then comes back down. Now, the position versus time graph, at time equal to 0, we had the position equal to 0. So we have time equal to 0, position equals 0, then it goes up and it comes back down. Careful here, although this looks like the path, the trajectory, this is actually a position versus time graph. So this is just showing that it goes up and then it comes back down. The velocity versus time graph of this, then it starts out at a positive 13 meters per second, and the acceleration is a constant value, so we have a constant negative value, so we have a constant negative slope here. And so we can see that this this point right here, at some point the velocity will be equal to 0, and if we just look at the equation here, we'll have v is equal to v naught, vy is equal to v naught y plus ayt. And so the velocity at some point later, vy will be 13, and then minus 9.8 times the time. So clearly, at time equal to 0, we had a positive velocity, but there will be some time in which the velocity will become negative. The point at which the velocity becomes 0, we defined previously to be the top of the path. So we could set this equal to 0, and we could find out how long it takes to get to the top of the path. Just 13 divided by 9.8. And so we'd have here, this is our velocity versus time graph, and we can tell the top of the path much easier on a velocity versus time graph because it's where the velocity is 0 than we can on the position versus time graph. And again, our acceleration versus time plot, this is a constant negative 9.8. If we were to, instead of throwing the ball upwards, if we were to throw it downwards instead, like we have over here in figure B. So it starts out at a y equals 0, but the initial velocity is downwards, 13 meters per second. So what that would change here, that's not going to change the acceleration at all. So this acceleration versus time graph is going to look exactly the same. However, the velocity versus time graph, the slope of it won't change, but our initial velocity will, right? This will be a negative 13 as opposed to a positive 13. And so then for B, I'll just sketch it over here on the same graphs. The way B would look is that it would start out at a negative 13 meters per second and then have a constant negative slope, and the value of the slope being negative 9.8. So this would be the velocity versus time graph for picture B there, with the ball being thrown downwards. Similarly, we would have the position. It would not actually go up at all. It would only go down, right? So although the position still starts at 0, it's going to have the same quadratic slope here, this curve to it, and it's going to have a negative initial velocity, so it's going to be coming down very quickly like this, right? So it's going to be very steep in the downwards direction for the position versus time, instead of it going up and curving. But it'll still be this curved. Just to exaggerate here a little bit, it'll be something like this. Okay. Similar, I guess, to the one that's dropped over here, but it would be a little bit more pronounced because you had the initial negative velocity. So free fall is simply a state of something falling. It doesn't have to just be falling. We could have given it an initial velocity, positive, negative, and it's falling only under the influence of gravity, which means that the acceleration in the y direction is equal to downwards 9.8. So here we have, if we have free fall conditions, what it means is that the acceleration in the y direction is equal to 9.8 meters per second squared downwards. So positive or negative based on our sign convention we choose.